Okay. Hey, everybody. My name is Brooks Howe, and I'm going to be talking today about some machine learning methods that I'm using for my research. And yeah, I'm a graduate student at Auburn, so hence the Auburn slide. Yeah. Okay, so let's go ahead and dive right in. So I'll just give you a brief outline. The basic idea behind this will be I will try to give about a 40-minute-ish presentation, I think. And maybe 30 minutes. I'll try and keep it short. Take any questions at any time, so please raise your Zoom hand or type a question in the chat. I will continue to send this link in the chat. It is a Colab link, Google Colab. If you do not have a Google account, that's all you need to view this link. So you can go ahead and click it now and pull up the code that I'm going to be working through. That will be towards the end of this workshop. And that link is a view-only link, but when you open it, you should be able to create a local copy on your own Google Drive that you can then edit and follow along. I just don't want everybody obviously editing the same document. Obviously, that would be a mess. So yeah, and if there are more people who arrive, I would ask if Jackie, if you could resend the link that I've been sending, that would be awesome.
Yes, I'm happy to do that.
Okay, thanks. Okay, great. So I'm going to start with about me, some about me stuff. Then I'm going to talk about some plasma background because that's the type of research that I do, dusty plasma. Then I'm going to talk about the main idea of today's talk, which is the sparse identification of nonlinear dynamics algorithm or method. And then we'll dive into some code for a minute. And then we'll jump back to the PowerPoint and I'll talk about my specific research problem that I've been working through recently. So starting with the about me, I have a small collage. So I'm a part of the United Campus Workers, which is a labor union. We're very active at Auburn. We have a petition for a living wage. That's one of my I guess passion projects, if you want to say that. This is me at my graduation. I'm also a pianist. I got a degree in music for my undergrad as well as physics. I like doing outdoorsy stuff. And here's me presenting pretty much this work at the latest Division of Plasma Physics conference for APS. And then my cat, of course, obligatory cat photo where he's loafing. I also wanted to go through some acknowledgements. This is my research group, my advisor, Eva Kostadinova, and we have graduate students and undergraduate students that help us with our various different projects. It's a great group to be a part of. We're called the Interdisciplinary Plasma Lab. And I also have another acknowledgements slide, which is just so the grants that fund this work from NSF, NASA, and the Department of Energy. And I also want to put in an acknowledgement to the experiment we use, which is the Plasma Crystal 4 laboratory on board the International Space Station. And then there's some names of our Auburn University collaborators, as well as we have Baylor University collaborators. So I just wanted to highlight those collaborations when I talk about this work. So getting into the content of the talk here, I again want to encourage questions to be asked at any time. If you have them, just raise your Zoom hand or throw them in the chat. I want this to be interactive. So I'm going to start with talking about dusty plasma, if you've not been exposed to it at all. This is not a section of the talk I usually give in Auburn, because whenever you hear this, what is plasma talk in Auburn, everyone groans because they've heard it a million times. But given the broader audience here, I wanted to just go through some basic plasma stuff here. So I wanted to talk about, plasma as the fourth state of matter. So plasma is abundant on Earth and in the universe. And so I have some fun pictures here. Plasma can be thought of as an ionized gas. And, you find it in lightning. You find it in the interaction of the sun's charged particles, streaming charged particles known as the solar wind with the Earth's magnetic field. A huge application of plasma, especially in and also where our funding a lot comes from is in fusion energy research. So this is a picture of a tokamak, which is a type of fusion energy device that uses plasma to try and achieve fusion that has a net gain. And then I also have this picture of neon sign, which is actually the most similar as far as the type of plasma that I study is most similar to the type of plasma that you would find inside of a neon sign like this. And then, of course, plasma is even more abundant in the universe than on Earth, at least fractionally. So I think the statistic is something like over 99% of the matter in the observable universe is in the plasma state. Just kind of a fun fact. And so I have a picture of a star, I have a picture of a nebula. And does anyone know what this picture comes from? Out of curiosity, the bottom one here.
Black hole accretion disk.
Yes, so it comes from a movie.
Interstellar.
Oh, Interstellar.
Yeah, Interstellar. So anyway, yeah, so it's a black hole accretion disk, which is another example of plasma in our universe. However, I want to hone our discussion in a little bit more on the types of plasma that we study, often referred to as a low temperature plasma. Low temperature is generally to differentiate it from a high temperature, which is used for fusion applications, plasma. Low temperature plasma is more like the ones you would find in a neon sign, like I showed on the previous slide. And generally, you're talking about 3 species present. So there's going to be some gas, and in the low temperature plasma setting, we often use some noble gas like argon or neon. And so notably, you get a lot of neutrals still left over. So you're ionizing some particles, creating ions and free electrons from that ionization process. However, you also are left over with a lot of neutral particles as well. In the sun, you're going to be a lot less neutral particles, right? That plasma is so hot that there's very few particles which are not ionized. We also are in a collisional regime. High temperature, a lot of things, they're moving so fast that they don't collide with each other. But when you're low temperature, you're having a lot of collisions, particularly with neutrals and ions. And like I said before, low temperature refers to the fact that it's not fusion plasma. It can be found on the edges, for instance, of fusion plasma. But the main interest of nuclear fusion plasma is very high temperature systems. And we usually use an inert gas, very, very often, neon or argon. An example of this is the fluorescent light tubes, which are becoming, less and less popular in favor of LEDs, but you've probably seen them before. And this is a cool picture where of the experiment that I work with data from. And this red glow is from a neon glow discharge plasma. The green glow comes from an illumination laser. So that's just kind of a cool picture of the experiment. So what is a dusty plasma? I talked about low temperature plasma. A dusty plasma is referring to the same low temperature plasma system. However, I put in particles, which I have on the order of 10 microns here, but you can get nanoparticles, which would be on the order of, between 10 nanometers to 10 microns. And so you can get a lot of different sizes of particles. But for us, we focus in the range of 1 to 10 micron diameter particles. And when they enter the plasma, so the orange ball here represents a dust particle, which generally those are made out of those are made out of some type of plastic. For our case, we use melamine formaldehyde. And when it enters the plasma, it immediately starts picking up charged particles from the background plasma. Of course, these are much, much larger than both ions and electrons. And so they can pick up a lot. Generally, they pick up more electrons than ions because the electrons are quite hot. And in a low temperature plasma like we're talking about, it's very interesting because the ions usually remain about room temperature, and you treat the electrons as an entirely different species, which get much, much hotter and have a lot higher thermal velocity, and thus will get onto the surface of the dust particle. So they generally become negatively charged because of that. And dust charging is a very dynamic process. A lot of times in scientific works, we consider the charge of the dust particles as being constant, which we'll do in this work. But I just wanted to point out that it's a lot more complicated than that. You can get this secondary electron emission, thermionic emission, where the heat of the dust particle might get rid of electrons, or you can actually take electrons off with a photon, which happens a lot in space, as you might imagine, when there's lots of stars. And one of the benefits of having a dusty plasma, or why we actually study dusty plasma, is that the dust can be illuminated with a laser. And that size of the dust being, 10 microns, 1 to 10 microns in our case, that allows for very easy observation with just a normal camera. Very, very simple observation. You can see with your eyes as well. And so, you can't see ions and you can't see electrons, but we can see the dust particles. And because the dust particles become charged, they interact with one another. A particle at very far from another particle, their motion all affects the rest of the particles in the plasma because they're all charged and they experience long-range Coulomb effects. And so the system can be used to the study of collective effects in strongly coupled systems, because a lot of times strongly coupled systems, like in materials, the individual constituents of the system will be, you can't see them. You have to use some complicated diagnostics. Well, here we can just look at them, take video of the individual constituents, which is really beneficial for studying these collective effects and allows us a unique window to study those. In many other systems, you can't directly see what's going on. I also wanted to point out we have the this is a Coulomb interaction. So potential V as a function of R this is the Coulomb potential times an exponential decay, where this lambda D is called the Debye length, and it's just a characteristic decay length. And this is generally in an isotropic plasma, or in other words, a plasma that doesn't have a preferential direction to it. You get this type of interaction between dust particles. And we're going to be talking about one of the things that motivates my work is that this does not hold in all plasma situations. Most plasmas are not anisotropic. Most of them, I shouldn't say most, but a lot of them do not. And so that creates complications we want to understand better. To do that, we use machine learning methods. To use a buzzword. To use less of a buzzword, we use data-driven approach. And in particular, we are looking at using the sparse identification of, we have been using the sparse identification of nonlinear dynamics. So I want to talk a little bit about where that sits. So this kind of sits in a broader category of machine learning for system identification. For system identification basically just means I want to understand my system better. And so what machine learning tasks can I do to sort of distill some physics from my data? And so I want to talk about how that fits into this whole science picture, which is, I think, a really interesting topic. And so this is machine learning is the buzzword. I think a more correct term is data-driven discovery or data-driven analysis. And it's been called the fourth paradigm of scientific discovery. There was this book, I believe the book is just called A Fourth Paradigm, and it was released by like a group of Microsoft researchers, where they say we're in the age of big data, and we need new tools to investigate all the data that we have. And we call this the fourth paradigm. But to make sense of this, of course, we need to talk about what are the first three paradigms. Well, you'll find that they probably are more familiar to you than you might think. The first paradigm of scientific discovery in this kind of picture is empirical experimentation, where I have a system that I want to investigate. So I look at the system, I observe the system, I make measurements, and I see what's going on, so it's just the observation of the system of interest. And the next paradigm is the analytical derivation, where I basically say I have this overarching mathematical model or theory that I use to describe a system. And can I make from the overarching governing laws of that theory, can I do some mathematics to come up with something in my specific case, right? So that's analytical derivation. And then with the advent of computers, of course, computational investigation or simulation has become extremely important, where I can use, again, first first principles approach where I take, I say, I know how two charged particles interact. Now, let me imagine that I have a bazillion of them, right? Let me make some complicated simulation where I at least get closer to explicitly simulating the interaction of each individual constituent. Right. And numbers 2 and 3 on this list are basically two different ways to get me from first principles to being able to predict or understand a specific system's evolution in time or space. Right. And so analytical derivation gets me there through some kind of mathematical deduction, whereas simulation or computational investigation gets me there through simulation. Yeah, sorry, I misspoke there a little. But yeah, so it gets me there through simulation, right? So I can say that I know how things like this basically work from the theory that I have, and I can do a simulation of my particular case to try and understand what's going on. And then generally I compare that to the observation, right? So I have some experiment and I say, oh, I did some math and it gave me this prediction. Well, how does that actually look when I look at the data? Is the data that we're observing obeying the relation that I derived? Similarly with simulation, is the simulation doing what the observed natural system does? And so the idea behind what I'm trying to get with this slide is there's this fourth paradigm of data-driven discovery where this is sort of a top-down approach. Top-down being I work from the most general to the more specific. Okay, this fourth paradigm here, data-driven discovery, takes me from the low level of specific data from a system, and it takes me back up to first principles that I might not even have. Or it takes me up to a prediction of maybe a more general system. So the idea behind this is instead of going from first principles to prediction, I'm going from data, which I get from observation, and I'm getting to a prediction or a new understanding of system dynamics. And the way that I do that in this picture is through optimization. So that's sort of the big picture frame for what I'm talking about today. We are trying to do this analysis of data that will give me a prediction. And this is sort of a bottom-up approach as opposed to these top-down approaches of simulations and analytical derivations, right? So the sparse identification of nonlinear dynamics is the method that we're going to be talking about, SINDY for short. And it's an open source statistical learning, as opposed to machine learning method, which was originally published in 2016 by a group at the University of Washington, where they said the key observation for them is that many dynamical systems have a few important terms which govern the dynamics, right? So I want to avoid an extremely long and complex description of something if I can have a more simple explanation that might not be the most accurate model possible, but it might generalize better. And the way it does that is it uses this method known as sparse regression to distill governing equations directly from data, right? So instead of going from an overarching model to get some prediction that of governing equations for a specific system, again, I'm going back from data, which is as low level as you can get, and I'm trying to find those governing equations. So this idea here comes from many systems are governed by dynamical equations of the following very, very general form, where I have the time derivative of this vector x. This vector x would be some vector which describes the state of the system at time t. And here, vector, all we mean by vector is just a list of properties of a system that I can potentially measure or derive from measurements that describes the system that I'm interested in at a given time. And I take the time derivative of that and say that it's equal to some vector function that describes the system dynamics. And the idea is I can learn ordinary differential equations, or ODEs for short, to directly from data. using this sparse identification of nonlinear dynamics method. Mathematically stated, I can determine this function, this vector function f, and I can get a system of first order ODEs in terms of the elements of x, right? I also wanted to just point out that we're going to use dots to go forward, and that just the dot is referring to a time derivative. 2 dots is the second order time derivative. Just to convince you that these kinds of kind of equations exist, the most possibly one of the most used systems of equations, especially in mathematics, applied mathematics, it seems to me, is this Lorentz equations system, where I have 3 different coupled differential equations here that lead to chaotic dynamics, which are interesting and hard to predict. Another one would be, this would be a little bit closer to physics, which you might be more familiar with, I'm certainly more familiar with, is like viscous air drag, right? So I have the force ma on the left, where a is just v dot, or the time derivative of the velocity, and that's equal to gravitation, the gravity's force minus this quadratic drag. And so these kinds of systems of equations exist everywhere around us, right? And have been studied for many years. So the idea is, can I discover these ODEs, these ordinary differential equations, as a linear combination of nonlinearities? Maybe I have some data and I don't exactly have a great description in terms of like an ODE that is of the form that we discussed. Can I get that directly from data? And so the idea here is, okay, I have some feature or state of a physical system as a function of time. This could be position, velocity. This could be pressure, temperature. This could be any feature of interest, right? That we think would be present in a differential equation that might govern the system of interest here. And that's equal to a sum. And the sum is consisting of these nonlinear basis functions that could describe dynamics of the physical system. And the idea behind this method is that you can determine which functions you think would best describe this ODE, okay? And written in vector form, that looks like this, where I have this vector x, which is just a list of features or a list of things. It could be, for instance, x position, y position, z position. So it could be three features. And that equals this coefficient matrix times this vector of basis functions. So this is just another way to express the left-hand side here. And the idea is that each of theseCij's, which fits into this matrix, will scale the basis functions phi sub j, and tell me which of the phi sub j's are most important to describe dynamics of interest. And the way that this is formulated in the Cindy terminology, right, is, let me actually, what I want to say is the way that we do this on real data is we take discrete measurements of things, right? So if I have x position, y position, z position, in reality, I'm not going to have a continuous function that describes those positions. I will have discrete time measurements. So at timestamp 1, I sample x, y, z. At timestamp 2, I sample x, y, z. Well, what we have to do with all those numbers that we get is organize them into a big matrix. And that's what you see here. And the dot, again, represents the time derivative. And so that's a matrix of discrete data measured at different time steps and then numerically differentiated. And that's equal to the right-hand side, which is just the library of basis functions, which is calculated from data at those discrete time steps. And again, that gets multiplied by this matrix of constant coefficients. Okay, so another key point that I want to make about this is that how does it actually find this matrix C? And so this is the way that you pose the problem mathematically. You say, okay, I just go back for a minute. This equation is what I want to be true, right? I want x dot to equal phi times C transpose here. Well, and I'm trying to solve for C. I know phi and I know x dot. Well, this is a massively overdetermined system, which means that I actually cannot get x dot to perfectly equal phi times c. But best I can hope for is to minimize the error, or to get x minus phi c as close to 0 as possible. And that's what this first term is actually doing. Another word to describe this is least squares regression, which is exactly what Excel does when you say plot me a line of best fit, right? And so, and it uses the so-called L2 norm, and the L2 norm is just the normal. I shouldn't say normal. The L2 norm is just the usual vector Euclidean distance norm. So I have a vector, and I take the sum of the squares under the square root. I'm squaring it here, so it's just the sum of the squares. So that's why it's called least squares regression, right? And then the second term here is doing this thing called promoting sparsity. And how does it do that? Well, I have a solution C here, and that solution C, I take what's called the L0 norm. And the L0 norm is very, very simply the number of non-zero elements. Okay, and so what this essentially does is says argmin here says that I'm trying to minimize the stuff in the big parentheses, right? Trying to get that as small as possible. Well, we already talked about why we want to get this term small. But if we go back to what I said at the beginning, is that we want to discover parsimonious equations, right? Parsimonious equations will have most of the terms of our nonlinear basis, right, that we've determined. We want those to be 0 because we want the simplest explanation of the system at hand, of the system of interest. And so the way to do that, one way to do that mathematically, is to say I'm actually going to penalize solutions that have more non-zero elements. And so if C has a bunch of non-zero elements, this L0 norm term will be maximized, right? And that's going to be penalized in this minimization problem. This whole step over here is called regularization. Okay, and so regularization essentially says I'm specifying the type of solution C that I'm going to get from this optimization. And then the lambda here is called a hyperparameter. And that means that I can actually just pick this. This goes from 0 to infinity. I can pick any number here, and this just weights this term, right? So if this is 0, I'm just doing least squares. And then as I increase my lambda, I get sparser and sparser solutions that give me simpler and simpler explanations of the data. And so I'm penalizing those solutions and getting more sparse solutions. And so again, a sparse vector or matrix has mostly zeros and only a few non-zero terms, which is exactly what I want, because the idea is that systems are usually governed by only a few dominant terms, and I only want to know those to get my explanation. The method that actually PyCindy, the code uses, is this sequential threshold least squares, where it just does the least squares regression here. So there's no second term as we had on the previous slide. And the STLSQ here, the sequential threshold least squares, is kind of what it sounds like. I perform a least squares regression, and then I say, okay, let me look at my solution C. My solution C has all these coefficients. And what I do as a practitioner of this method is I say I set a threshold and it says any element of the matrix C below the certain threshold, I'm going to just force it to be 0, and then I'm going to do the least squares again, while forcing those ones that I already set to be 0 to stay at 0. And I iterate on that loop here until none of the coefficients in C are below the threshold, and then it converges, right? So that's the idea about how you can get a more sparse solution. So I'm trying to get, again, I'm trying to get a matrix C which has as few terms as possible that still well describes the system. Okay, so now I want to get into the code a little bit. So that we can have some interaction going on. So this method is all written in an open source code available on GitHub called PyCindy. And they have this wonderful GitHub page. I cannot stress enough. If you want to learn more about this method, go to the GitHub, because the GitHub has a ton of examples built in. and you can go and run things and see the full functionality. We're going to go over today a very small subset of the functions that PyCindy has available. But it has many optimizers, many libraries of terms. Those are the nonlinear basis functions that I mentioned, and different optimization methods that you can use. So with that, I want to go into share the code. So if you pull up your if you click on the link that has been sent, you should get something that looks like this. And can everyone still see my screen?
Yes.
Okay, thank you. So when you pull this up, it should look like this, except you'll have a box here which says something like save to drive or something like that. You'll want to click that so you can actually edit this document, because it's a view only with the link that I sent. So you want to make essentially a local copy of this notebook. And then we can go through the different cells here. Okay, I'm just going to give it like 2 minutes. Is anybody having trouble finding it?
Working for me.
Cool. Okay, so you can also open up this table of contents on the left side, which is helpful for quick and easy navigation of this document. So I just wrote some of this code and pulled some of this code from the GitHub that I mentioned, as well as from this YouTube PyCindy tutorial that I've linked at the top. Highly recommend this. I think this one links the playlist from Alan Kaptanoglu, who spent a lot of time making a really useful tutorial on how to use this method if you want to spend more time in going through exactly how it all works. I've got 2 references here. The first one is the original Cindy reference. The second one is the code reference. And then I've also shared some resources here, which are the textbook that Stephen Brunton and Nathan Kutz from the University of Washington have written. This is an extremely helpful, pretty accessible introduction to data-driven approaches to science and engineering, as it says in the title. This is where I've read a lot from this book. It's been extraordinarily helpful for me. There's a free PDF available at this link. The textbook has its own website where it has lecture videos associated with every chapter, every section of the book. It's really great. It gives you a nice broad brushstrokes overview of some data-driven approaches. This is the YouTube playlist that I talked about before, and this is the GitHub. Okay, so to start going through the code, the first things are boring, right? So this first line will install the PyCindy package, which if you wanted to do this, if you were using this method, this is what you would type into your command window. If you know how to use pip, you can just install PyCindy with pip with very simple pip install PyCindy, and we actually need to do that in Colab because PyCindy is not preloaded. Apparently, in Colab you can put this exclamation point first, which basically tells it that this is a command line, not Python code. Okay. Is anyone having trouble with that? Because if you don't do this, nothing will work. Okay. And then, the next 2, we'll just need to run those, import libraries, and then I've written a function here that we'll use later. All good? Can also react with thumbs up. Yeah, I can see those. Okay, appreciate it. Thank you, Juan. So the first example I wanted to give is something that I think everybody can relate to if you've done introductory physics. So And this is, not the most ideal scenario for Cindy. This isn't like a research relevant question, obviously, but I think it illustrates exactly what's going on to a certain extent here. So basically what we want to do is you want to imagine throwing something up in under gravity on Earth, right? This could be a shooting cannon straight up. This is all going to be one-dimensional, right? So it's not even projectile motion, it's just straight up. So this is the example I want to do. And right, we know that from Newton's law that we have a differential equation from Newton's second law, F equals ma, right? My double dot, y would be the vertical position here, is just equal to negative mg, which is just the constant gravitational force if you're near the surface of the Earth, right? So what we want to do with this is we want to simulate a trajectory in space and in time of what that would be doing. And to do that using SciPy, we'll use this scipy.integrate.solve underscore IVP, which is IVP is initial value problem. So you're going to give it some initial conditions. And you get a system of equations which looks like this, right? Because I can take the second order differential equation and make it a system of first order differential equations, which is the type of input that this solve IVP takes. This is the type of input that PyCindy takes. And so the way to do that is just by introducing this variable v sub y, which we know to be the velocity, right? So we have y dot equals v, very simply, v dot equals a constant, negative g. And then in the code, position and velocity will be stored as in a NumPy array. So that's the first row of that array will be this y0, and the second row will be y1. The first row will correspond to the position and the second to the velocity. So you can go ahead and run this cell, and I'll walk through what it does. So up here, I'm just defining initial conditions or simulation conditions, I guess. So my time step will be 1/100th of a second, and we'll simulate for 5 seconds. And we know G is 9.8, not negative 9.8. If you told our lab manager that it's negative 9.8, he'd have your head. And then you can define a temporal grid on which to calculate trajectories, which is just done by this numpy.arange command. So it'll basically create a list of numbers from 0 to 5 seconds with 100th of a second increment in between. And this is just telling you what's the first and last as a tuple in Python. And then the way that you define the equations of motion shown up here, right, is by defining just a normal Python function. So that I've called it upward cannon. So you can think of a cannon shooting straight up against gravity. And why does it look like this? It returns two things, okay? And the reason it does that is because it takes equations in the form of this first order system of ordinary differential equations, right? So the left-hand side is baked in essentially, and what I'm putting in this return is the right-hand side. So as I said, this y1 will be the velocity, and so that's why it's the first one here, because this is telling SciPy that y dot is equal to vy, which in the code is represented by y with y1. And then v dot is going to just be negative g. And so that's how you put in this system of equations into it. And then I've also defined another function, which is just hit ground, which is just returning the positions. And I'll show you why that's important in just a second. Here, in this 3-line block, we are solving the differential equation system that we put in. Of course, we know this is we know that this is a very deterministic system that we can solve by hand, but this is how you generally can generate some trajectories by doing this numerical integration tactic using solve IVP. And so you actually put in the upward cannon function as the first input, and then you tell it some other things. These are the initial conditions, which would be we start at 0 and we start with initial velocity 10 meters per second up. And then I tell it the temporal grid that I defined up here. And I also define this event, and all this does is it uses this, and when the position hits 0, it will stop the solver. And so we get these nice, so this is just extracting the data, and this is the nice trajectories we get that you would have seen in Physics 1 as a freshman or maybe a high schooler. And so you can see here, I get a parabola of y versus t, and I get a line for velocity versus time, right? And this is nice and all, but in real life, we're going to have data which is noisy. It's going to have some measurement error to it. And so what we want to do is actually add some error to the data, add some measurement error that would be simulated to the data. And the way that we do that is by using a random number generator in NumPy. And so here I'm transposing the solution so that it looks like this, where I'm switching from Y to X. So this big X matrix will be, first column will be the position, second column will be the velocity. And that in the code will be represented by X underscore train. I also wanted to, is there any questions at this point, or is everything working? Is anything not working? Great. Well, again, raise hand if you have any questions. So what we do here is add some noise to the data. And the way that I'm doing that, I'm just saying, calculate the root mean squared error, and that with respect to, or compared to a matrix of just plain zeros. And so I can get like the geometric average of the data so that I can then add noise. So this gives me the RMSE, the root mean squared error, which just kind of gives me a general feel for what's the magnitude of the numbers in the data. And then I can say, I'm going to add normally distributed random numbers to this data, and it's going to be the same size as the data here, and the noise level will be scaled by this RMSE that we calculated, just so that it's kind of comparable. And so here I've set the noise level to be 1%, 1% of the RMSE. And so when we do that, and we plot, the data sort of looks like this. And you can see here, you have like a jagged line. The blue line would be the noisy data. The red line would be the clean data. And you can see that there's a little bit of noise added to it, just a very little bit at this point. Okay, and then just to give you an idea of how easy it is to run Cindy, this is what is this? 5 lines really, of code is what you need to run Cindy using PyCindy. So we imported PyCindy as PS, and so that's why you see this PS prefix here. And if we run this, we get this very simple output. And if we look at this, so if we look at the code, this is me telling the feature names to Cindy. I say, call the position Y, call the velocity V. Then I define an optimizer, which, if you remember from my presentation, we're using the sequential threshold least squares optimizer. And then PyCindy is written as an object-based code. And so basically what that means is that I can define this model as a Cindy object. And the way to do that is to say model equals PyCindy.Cindy. I pass the feature names, and I pass the optimizer. The optimizer we're using, again, sequential threshold least squares. Once I have my model, I say, model, I want you to fit to this data using this temporal grid. It does that, and then I can just say print. And you can see here that it actually gives me the close to the correct differential equation, which I use to generate data. And so, yes, question.
Sorry, could you repeat what the threshold is exactly? Is that the regularization parameter, or what is that?
Yes, thank you. Good question. the threshold for for the sequential threshold least squares, that's like I take all the numbers in my regression coefficients that I get, and I say everything below the certain threshold set to 0 and redo least squares. And so that's the hyperparameter that I have for this method, sequential threshold least squares. And so you can go through and change this threshold. Here I just have it set at 0.5, but the idea is that you can change it and tune it so that it can give you different solutions. So for instance, if I set the threshold equal to 0, that's equivalent to just doing least squares. And if I run this code with the threshold equal to 0, you'll notice that I get these really complicated, thank you, Daniel. We get this really complicated looking differential equation, which definitely does not describe my data well. And you can play with this, and I'm going to have each person play with this for like a couple minutes. But the model that Cindy gives you is extremely dependent right on the threshold parameter. So you can play around with it and see where you get better models or worse models. And another question that naturally comes up when you do this, oh, what are the basis functions that I'm using to describe the data? Or what is Cindy using to find these basis functions? So you can say, hey, wait a minute, what are the features that I'm trying to use to describe this differential equation? And it'll tell you, this is the default. So these are just the default basis functions. I have unity, a linear dependence, and then quadratic dependence. So it's a polynomial basis up to order 2. And you can see, if I have threshold equals 0, it uses every single one of these basis functions, right? So it says y dot is equal to something times 1, something times y, something times v, etc. Uses all of the basis functions available to it. But as soon as I start promoting sparsity via this threshold, it starts cutting out certain terms in the basis. And that's the crux of the Cindy method. It uses this optimization to make a sparse solution. And then I just have one more cell to run, where I can take the data and predict, using the model that Cindy discovered, what the derivatives will be. And so here, this would be my y, and x1 here would be my v. And so you can see that they line up pretty well. The model predicts versus what the finite difference method gives us from the original data. And you can see that they line up. But if I were to go back here, change it to 0, and recalculate this, you can see that the model that I get from Cindy isn't, in the first case, it's lining up pretty decently well, but it's certainly overcomplicating things, right? I have a bunch of quadratic terms. Whereas down here, it's just supposed to be a straight line, and it's giving me this weird quadratic term. So yeah, so that's another thing you can do with Cindy. So now with this time, for the next couple minutes, I was going to let everybody go through, and if you want to mess around with this, go through and change the following 3 parameters. The dt, which was in the simulation cell up here. So that's this first number. And then the noise level you can mess around with, which would be this term. And then down low, down in the Cindy cell here, right here, you can mess with the threshold. And just mess around with the numbers, change the numbers, and see how you can get better or worse solutions for different parameters. So I'm going to give like a couple minutes for people to go through and mess around with that. Yeah, question.
This might be something you want us to discover, but I was wondering if it seems from playing with the threshold that the coefficients are not normalized, right? Ideally, one of the coefficients is 1 and the other one is like close to 10. And so if I set my threshold anywhere between 1 and 10, that's gonna eliminate the possibility of the true solution of the actual equation with a 1 and a 10. So is there a way to normalize the coefficients?
Yeah, great question. Yes. The way that you can do this is by normalizing not the coefficients, but normalizing the basis functions. And you go through, and they talk about this in the Cindy paper, along with the supporting information appendix, about how you can go through and normalize things so that the coefficients that you get or that you want to get are on the order, 1 to 10. And then you can mess around with thresholds a lot easier, because if every time you're trying to get coefficients that are 10 to the -3, 10 to the -4, it's going to be a lot harder to mess around with those numbers, and it just doesn't perform as well down there with those tiny numbers. And so you want to normalize and I'm not showing that here, by the way. So this is something you would do if you were applying this to research. You could normalize the basis functions so that they all have comparable magnitude. And then you can do that in a way that makes theoretical sense, using intuition, stuff like that. Does that answer your question?
It does. Thank you. That
Cool.
makes a lot of sense.
Yeah, cool.
Also, separate question. So from your slides, there's a theoretical equation that we're solving regularized least squares,
Yeah.
where there was a lambda regularization parameter. But I
Yep.
notice in the code that's not explicitly stated because the method that we're using is the sequential threshold least squares.
Yep. Exactly.
Is there an implicit lambda, or do we just not worry about it?
Yeah. So that with the equation with the lambda, that is basically the most general way to pose a sparse regression problem. However, you can do it in a number of ways. And what we're doing here is, instead of putting it in the objective function or in the loss function itself, we enforce it after we do least squares. So you do it in 2 steps. There are many ways. Sequential threshold least squares does not do this, but something like there's an optimizer called the lasso, which is the least absolute shrinkage and selection operator. And that one uses the L1 norm. And instead of the L0 norm, like I showed. And that one, you actually have the ability to change lambda, make it higher or lower. And you can use lasso in PyCindy. It has it built in. And so if you go to the GitHub, you can look on a couple of the different Python notebooks that it has there and see how to implement different optimizers. Lasso is going to be one of them. There's a number of different optimizers that they use. It's just so happens that the optimizer, the STLSQ optimizer, does not utilize that lambda. Instead, the hyperparameter is the threshold.
Gotcha. All right. Thank you.
Are there other questions? Be happy to take any questions. Has anyone gotten some interesting results from messing around with the numbers here, DT, noise level, threshold? What happens if go ahead?
Oh, no, I was going to say I was able to get close. It's like 1.2 and negative 10.2 are the coefficients I'm getting with using 10% error, which was, I think, very generous.
Yeah. Cool. So I also wanted to demonstrate if I decrease the time step, I get a lot more noise. Well, I get a lot more time resolution in my data, right? And it definitely changes the solution that we get for the same threshold. So if I can increase this threshold a little bit more. And you can start to see that sometimes when you make the threshold too big, you start zeroing out everything. You get bad models that way. And then Juan, you said you didn't change the time step, but you changed the
error.
To 10%. Oh, I didn't run the first cell. It's gonna yell at me. Yeah, so we could get some nasty looking trajectories here. Yeah, is that about what you got, or?
Yeah, that's exactly what I got.
Yeah. So the reason it's exactly what you got, by the way, is because we're using a seed number for the random number generator. So all the
makes
random
sense.
numbers that everyone gets are the same random numbers. But if you were to do this with, yeah, it might be different. Anyway, yeah, you can do this. Also with higher noise levels, if I make it more of a coarse grain solution here, I'm just kind of testing this out, see if it does any better. No, it does worse. Okay. Sometimes when you decrease the resolution of your measurement, this is another interesting fact. If you decrease the resolution or downsample your measurements, for instance, so I take like 1 million measurements a second. Let's say I only want to take 1,000 of the measurements that I actually took and feed them into Cindy. That can improve the model because I have less chance to overfit. I'm just trying to show that here with some numbers, but anyway. So you can mess around with it. Okay, I have some more stuff to show. Jackie, am I supposed to be cut off at 4?
I think the idea was to go for about an hour, but if you want to go
Okay.
a little bit longer, that's okay. I don't know if folks here are.
Yeah,
able
if people have to
stay.
leave, that's totally fine. I was going to show some of my research stuff. So stick around if you would like. And I will just show that really briefly. Should only be about 15 minutes at the most, I think. So we talked about the code. Okay, so for our case, I gave some plasma background, but returning to this plasma system, the dusty plasma system, when you have an isotropic plasma where there's no preferred direction, particles in a dusty plasma will interact with this Yukawa or shielded Coulomb interaction. And again, the shielded Coulomb here would be, the Coulomb interaction times this exponential decay. However, in the presence of external fields, electric fields, we do get a preferred direction. And so the plasma becomes what we say anisotropic. And so the goal for my research project, is to use Cindy to determine the form of this anisotropic interaction. So this is just a picture of, what we call device shielding in plasma physics. And so this first case where I have no field, sorry, this is a little grainy. You have the negatively charged dust particle surrounded by a positive space charge. That comes from the plasma electrons being repelled from the negative dust and the positive ions being attracted to the negative dust. And so I get this non-quasi-neutral region around the dust particle, but it'll be completely spherically symmetric, right? In the case of no field. Now, when I introduce a direct current field into the plasma, an external electric field, I get this focusing of positive charge downstream of the dust particle. And so I have a dust particle which is negative, and if my field points to the right, the plasma ions will flow with the field, and as they find this dust particle, they will scatter towards the axis. of the flow, right? So downstream of the dust particle, I get these positive regions. And the positive region of one dust particle will attract the negative neighboring dust particle. And so you get this effect. And then if I have an alternating current field where the electric field switches from left to right, I can get these what we call ion wake fields, which is just this effect that I described where you have the the ions focusing and you get this positive region. Yeah, and so you can get these structures to form where I have ion wake fields on both sides of the dusts, and you can get these stringy structures to form, right? Thanks, Juan. And so one of the questions we wanted to ask for this research project that I'm doing is, can we learn the equations of motion for a simple shielded Coulomb Yukawa system? If you transform the Yukawa potential between two particles to equations of motion, I get this equation of motion, which I can then transform as we did with the projectile motion, the upward trajectory, into this system of first order differential equations. And going back to the code, that's what I've shown here. And so the system of equations that we're interested in is now this. This is not solvable analytically, right? So I can simulate a trajectory of position and velocity for those and add noise. And then I can actually define a new, this is defining a library of terms which is not baked into Cindy. And so I know that my equations of motion can be described in terms of these equations, of these nonlinear basis functions. And I just want to see if Cindy can pick out the correct ones. Here I'm going up to the fourth order rational terms. So this is how you define a custom library in Cindy. And you can see that if I add this much noise, this 5% level of noise, I can identify this is the correct equation of motion. So, oh, and this is, yeah, okay. Yeah. Anyway. So that's what I just wanted to show. That's how I actually apply this to research. I'm realizing I did not put the noisy trajectories in here. Here you can see if I add the noisy trajectories in the model, I get a little bit less accurate results because this is quite a bit of noise. So you can see how we went through and tried different hyperparameters with these trajectories to see if we could get Cindy to identify the correct model. So that's how I've been applying it to my research. Okay, cool. So I gave everyone this code. And I hope you guys can mess around with it. But that's pretty much all I had for my presentation.
Thank you so much, Brooks. This was a wonderful presentation. Very
thanks.
informative. I think most people here have said wonderful things, so they've had to leave.
Yeah.
Rohit, if you have any questions, please feel free to ask them.
Yes.
Otherwise, yeah, you are our last person, last one standing.
So.
And then I guess, great talk. Thanks. Excellent.
Thank you.
And then as requested, how did you find out about this type of research? Want to make sure that we get that in the recording.
Sure. So I found out about this type of research because my advisor had become interested in machine learning and was working with some people. They wanted to use computational simulation. They wanted to use experiments and machine learning, all to investigate this question of anisotropic potentials in dusty plasma. And there was pretty much like the older researchers who have been on this project for a while didn't have the time to really look into a bunch of different machine learning methods. And so they asked me to look into that aspect of the project. And so that's how I was basically started with this. I also knew that, this was before the 2024 Nobel Prize, but I also knew that machine learning was on the way up and becoming much more popular. And so I was sent some papers by my advisor, and she was just like, hey, take a look at these. And that's how I found Cindy. And I've been trying to adapt. There's tons of different types of Cindy. Cindy is like an expansive universe of different algorithms at this point. But yeah, that's basically how I found out about it. I think there's a strong desire for people to do more machine learning, data-driven analyses on things, because we do live in the age where it has tons of big data, and they are built for those problems. And so I was tasked to find out more about it. I think it's a great opportunity for graduate students, because a lot of times researchers don't have the time to look into a bunch of different machine learning things that they haven't heard of. And so it's a cool way to get exposed to it.
Thank you for that response. That actually kind of prompts another question. So the sizes of the arrays that you're using with Cindy, is there like a maximum, or like a way to kind of like, how much data is too much data, maybe, is my question.
Yeah. Well, it depends on a lot of things. It depends on how big your library of nonlinear terms is, because those can get huge, and that slows things down a lot. But with the size of terms that we're using, you can put. I haven't tested the limits, I should say. I should preface with that. But I think for a lot of these types of scenarios where you have, I mean, we did 1,000th of a second for about 2 seconds. It only gives us like 2,000 time steps per feature, so 4,000 numbers. But you can definitely do up a lot more than that. It will slow down eventually, but generally these methods are a lot faster than, for instance, training a neural network. These methods do very similar things to what Excel does to say, give me a line of best fit. And those algorithms are just very, very fast. So, okay, question.
Thank you. Yeah. Do you always select a polynomial basis, or it depends on the problem prior knowledge? Maybe some special functions may work better in certain problems, like Bessel function for a central potential problem.
Yes. Yeah, exactly. So the idea is that you use your prior knowledge to determine basis. So you can use pretty much any basis that you want. There's several baked in. I don't know if Bessel actually specifically is one of the ones that is baked in. I believe it's not. But they have the ones that are baked in is like polynomial, for instance, and sines and cosines. I think it's yeah, those are 2 ones that are baked in, but you can also go through and define your own, like I did for this last example. But yeah, the idea behind it is that it's sort of like physicist informed. You're using your physics intuition to determine what basis functions are going to be useful to describe this ordinary differential equation. And so yeah, so that was a great question, because that's exactly
And then I was asking because I felt like we might be biasing the results based on our priors.
Right. And we definitely are, which I think the statistics people and the math people might not like. However, in physics, we always do things that they don't like, first of all. Second of all, I think this is actually one of the benefits of the model, because you can actually use your intuition. Like, let's say there's been a lot of research done, for instance, in this field, on this problem, there's been a lot of research done. You can use our we can use our prior knowledge to come up with a basis that we would like. And so there is that inherent bias built into it, but ideally that is one of the benefits of using this method, is because we can actually say, no, we have a good idea of what the potential will look like. We just don't know exactly what it will look like. So we're going to use this regression method to find out which terms are most important.
And presumably you can always use experimental evidence to back up whatever you find from this.
Yeah, definitely. Okay, cool.
Yeah, probably it's a good time to call it here. Thank you to our one remaining participant, but thank you also to everybody that had come. Thank you, Brooke, so much for this presentation. It was wonderful. We do have a recording of this presentation, and we will post that on the APS YouTube site. And so in any case, I hope everyone has a wonderful rest of their day and weekend and coming holidays. And until next time.
Okay. Thanks so much, Jackie.
You're
Thanks,
welcome.
Rohit. Okay, bye.